All right. So mechanical energy and conservation. This is where we put potential and kinetic together to try to figure out what's happening in different situations. You'll find the math of this will just include things we've already done. So nothing that you haven't seen before, hopefully. All right. So mechanical energy. Mechanical energy, by definition, is the sum of kinetic and potential energies. Okay. So if we take the kinetic and potential energy of an object at any point in its path, whatever it is at that point, it'll be the same at a different point. Think about a ball rolling down a hill. The potential energy will go down, but the object will speed up, which means kinetic energy will increase, and they will bear each other out. In fact, energy of 1 and 2 are equal to each other, which means it's a constant. So knowing this, that total mechanical energy is always conserved, obviously is called the conservation of mechanical energy, if only conservative forces do work. Okay, so this goes back to conservative and non-conservative. So we're just talking about gravity here, no friction. The total mechanical energy of a system neither increases nor decreases in any process. It stays constant. It is conserved. And this is how we base a lot of things when we don't have those friction there. Now, we'll talk about friction, of course, later on, but just understand that here, no friction. So there's no non-conservative forces. Examples. We got water at the Yosemite Falls here, and that water's going down. Potential energy at the top gets transformed into kinetic energy as it falls. Obviously, some is lost as heat, and in the end, we don't get total mechanical energy being conserved because of the non-conservative forces. But potential and kinetic get conserved, they get transformed, I guess, from potential to kinetic. Here's elastic potential energy. When you pull back on a bow, this pulling back is giving potential energy to the arrow, and then it's going to be transformed to kinetic energy, because once this lady releases the bow, the arrow will take off with the velocity. So potential energy will be transformed into kinetic energy. And that's what we're looking at here, just this transformation of potential to kinetic and vice versa. Law of conservation of energy. True, the total energy is neither increased nor decreased in any process. Energy can be transformed from one form to another, but total amount remains constant. So even when we talk about forces that reduce mechanical energy, okay, and we call those dissipative forces, but when these forces reduce mechanical energy, just because mechanical energy goes down does not mean total energy goes down. You know, when you rub two objects together, right, and that friction is going to come off as heat. And so when we talk about friction and movement, we're going to see heat. And that heat energy, thermal energy that goes off, is what we call dissipative force. Okay, it reduces mechanical energy. We lose some kinetic energy because of heat. But total energy, kinetic plus potential plus whatever this other work is, this non-conservative force work, equals the total energy, because total energy always conserved. All right, so here's an example of a problem we could have. We have a baseball player, and he's hitting this baseball. We got the mass of the baseball here for a home run. All right, the ball leaves at the speed of 36 meters per second, and the fan that catches it is 7.2 meters above the point where it was hit. Now, we're not going to talk about friction here, okay, so we're going to get rid of the non-conservative forces. We want to find kinetic energy of the ball just before it is caught, and then the speed just before it is caught. So the first thing we want to do is talk about initial and final. So I got potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. And there's no work, so we're okay. And we want to look at this problem. We want to talk about potential energy to begin with. Now, we're calling this height 0. Okay, so that's our 0 point, which means our potential energy will be 0 initially. Our kinetic energy, 1/2 the mass of the baseball times its velocity squared. All right, so that'll give us an answer of 97 joules. Okay, so we have 97 joules of energy to start. Now, since there's no non-conservative forces, we should end with 97 joules of energy. Now, this energy is going to be split up from potential from height and kinetic energy from the ball still moving. So we're going to figure out what that is. So now our potential energy, final, is going to be the mass of the ball, 0.15, times Earth's acceleration due to gravity, and we multiply that by the height, which we said is 7.2 meters. And that's going to be equal, and plus kinetic final will equal that. Now, I'm going to do this math for you, and I get 11 joules. I got 97 joules equal 11 joules plus 1/2. 0.15, the final velocity of the ball squared. I can bring this 11 over, subtract 11 from both sides, and I get 86 joules is equal to 1/2 0.15 Vf squared. So I divide by this, take the square root, and my final velocity of the ball is 34 meters per second. Before with kinematics, we had to know the angle of launch, time it was in the air. We do all kinds of math. If we can get rid of friction, which we're doing here, and we did that and we did kinematics anyway, we can find final velocities a lot easier. Energy is the way to go to solve problems if we have everything we need. And that's what we get for the final velocity. All right, here's kind of a thinking problem. So we have two slides. We have one that goes straight down and one that has a little bit of a slope and does this. This one and this one are both the same height, okay? Oops, sorry. Same height. So the uniform slope versus the dip and leveling out, we want to talk about speeds. Which one is going faster? And I want you to think about this. You can pause this if you want to. Okay, hopefully you've thought about it. You come up with an answer. And the deal is this. Since our height's the same, potential energy for each of these swimmers is the same. Okay? Which means as they go down, their change in potential energy is the same. Okay? Because potential energy, mgh, with the height being the same, their kinetic energy at the bottom also will be the same. And so kinetic energy is 1/2 mv squared, 1/2 mv squared, which means their velocities at the bottom will also be the same. So we expect their velocities to be the same at the bottom of each slide. Now, if their masses were different, obviously that could have an issue, but you'd have to do the math to find out, wouldn't you? Okay, so let's look at this problem. We got a snowboarder, and he's in two situations. Here he's going 4 meters per second, and as he gets to the top of the slope, he stops. When he's going 5 meters per second, he gets to the top and he's still moving. So we want to know what the velocity is at the top, okay, of case 2. So the math of this, a lot of different ways you can attack it, right? Here's what I would do. I would take case 1 and find the kinetic energy at the beginning, okay? So for case 1, I go 1/2. My mass is 75, and my velocity is 4, okay? And I'm going to square that, of course. And I'm going to get 600 joules. So he has 600 joules of kinetic energy, which means at the very top, his potential energy, since he has no velocity, is also going to be 600 joules. Case 2, 1/2, 75, but now he's going to go 1 mile an hour faster, 1 meter per second faster to 5. That's going to turn out to be 940 joules, okay? So he has 940 joules of energy here. Here he only had 600. To stop, he'd have to have 600. So when he gets to the top here, he's going to have 600 joules of potential energy, okay? Which leaves him with 340 joules left over. So with 340 joules left over, we can find his final velocity just by making that equal to kinetic energy equation, because that 340 left over after that 600 is going to be kinetic. And when I do the math for this, when I divide and take the square root, I get 3 meters per second.